everyone, good afternoon. My name is Shweta and I'm an electronics engineer intern at Abhyas. And today's my topic is design of universal gates, NAND and NOR. Logic gates and its type. Logic gates are the important digital devices that are mainly based on the Boolean function. Logic gates are used to carry the logical operations on single or the multiple binary inputs and give only one binary output. In simple terms, logic gates are the electronic circuits in a digital system. So the logic gates are classified into basic gates, universal gates, and the special purpose gates. The basic gates are AND gate, OR gate, and the NOT gate, whereas the universal gates are NOR and NAND, and the special purpose gates are XOR and XNOR. So these special purpose gates are also known as application gates. We can use these gates in the application of full adders, half adders, etc. The overview of logic gates. Logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. So the relationship between the input and the output is based on a certain logic. AND gate. A circuit which performs an AND operation is shown in the figure. It has n input which has n is greater than or equal to 2 and only one output. So this is the symbol of AND gate. We'll be having two inputs and only one output. So the Y expression is A into B into C. So here there are only two inputs. So A into B is the Y expression. If there is more number of inputs, so A into B into C up to n number of inputs. So the truth table of AND gate. So if the two inputs are 0, 0, then the output will be 0. So the AND gate is a simple multiplication. So 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1. So this is the truth table of an AND gate. OR gate. A circuit which performs an OR operation is shown in the figure. It has n input, that is n which is greater than or equal to 2 and only one output. So we'll be having two inputs A and B, and this is the OR symbol, and the Y expression is A plus B plus C up to so on. As they here there is only two inputs, A plus B is the Y expression. So it is OR gate is a simple addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. So this is the OR gate. And the NOT gate. So a NOT gate is also known as an inverter. It has one input A and one output Y. So A is the input and Y is the output. So the Y expression is A bar. So A is 0 and B is 1, and A is 1, then the B is 0. So this is the OR gate and NOT gate. Next is the XOR gate and XNOR gate. So XOR is a special type of gate. It can be used in half adders, full adders, and subtractors. The exclusive OR gate is abbreviated as XOR gate or sometimes as XOR, and it has two inputs or more than two inputs and but only one output. So this is the XOR symbol, and the Y expression is A into B bar plus A bar into B. So this is the Y expression, and the truth table of an XOR gate is 0 into 0. 0 XOR is 0 and 0 XOR 1 is 1, and 1 XOR 0 is 1, 1 XOR 1 is 0. So this is the XOR gate. And XNOR gate is a special type of gate, and it is also used in half adders, full adders, and subtractors. The exclusive NOR gate is abbreviated as XNOR gate, and sometimes called as an XNOR gate, and it will be having the inputs n which is greater than or equal to 2 but only one output. So this is the logic symbol of the XNOR gate, and Y is equals to A bar into B bar plus AB. So this is the truth table of XNOR gate. A into B is if A XOR B. So 0 into 0, 0 XNOR of 0 is 1, and 0 XNOR of 1 is 0, and 1 XNOR of 0 is 0, and 1 XNOR 1 is 1. So this is the XNOR gate truth table. So now we'll be introducing the universal gates. So universal gates may implement any Boolean function without using any other type. So the NAND gate and NOR gate are the universal gates because they can perform all the three essential functions like AND, OR, and NOT gates. A two-input NAND gate is a digital combination logic circuit that performs the logical inverse of an AND gate. While an AND gate outputs is a logical one only if both the inputs are logical one, and then NAND gate outputs a logical 0 for the same combination of inputs. And a two-input NOR gate is a digital combination logic circuit that performs the logical inverse of an OR gate, while an OR gate outputs is a logical 1 if any one of the input is logical 1, and NOR gate outputs a logical 0 for the same combination of inputs. So this is the introduction to the universal gates. So NAND gate. So NAND gate is one of the universal gate. The NAND gate is an AND gate which is followed by a NOT gate. So thus we can see it is an and NOT operation. It may have two or more inputs but only one output. So the logical symbols of an AND gate at truth table are shown. So this is for the AND gate. If we add the NOT gate, then it becomes NAND gate. So the symbol bubble represents this is a NOT gate. So for the AND gate, a symbol bubble represents the NAND gate. So the expression of Y is A NAND B NAND C. If the two inputs are there, A NAND B is the output expression. So the truth table of a NAND gate is A into B bar. So 0 into 0, 0, 0 bar is 1. So again 0 into 1 is the inputs of A and B. So 0 into 1 is 0, 0 bar is 1. So 1 into 0 is also 0, 0 bar is 1. 1 into 1 is 1, 1 bar 0. So this is the truth table of the NAND gate. Next, the output is an exact inverse of the AND gate for all the possible input combinations in the NAND gate. So the OR gate with the inverted inputs is called as a bubbled OR gate or the negative NOR gate. So the NAND gate is also called as an active low OR gate. The switching circuit diagram of the NAND gate is shown below. So these are the two switches and there is a bulb. So here these two switches, if one is on, then the output is high. And if the 2 is on, so if the two switches are on, then the output is 0. So as the shown in the truth table, if both the inputs A and B is 1, then the output is 0. So here also when both the switches are on, then the output will be the bulb glows 0. The bulb does not glows. So this is the circuit diagram of the NAND gate. So the circuit diagram of the NAND gate is constructed using the PMOS and the NMOS. The PMOS in the upper stage is connected in the parallel and the NMOS are connected in series. So after connecting those, we need to give the connecting wire connections through the connecting wires, and we need to give the inputs and the here two inputs but only the one output. So this is the circuit diagram of the NAND gate. The simulation.
My topic is about design of universal gates, NAND and NOT. So first gate is NAND gate, and this is the schematic of the NAND gate. So to construct the NAND gate, we need to take the components selected are the PMOS and NMOS. So by using the PMOS and NMOS, we have constructed the NAND gate in the Cadence software. So to construct the schematic diagram of the NAND gate, first we need to go to the create instance to select the components. Click on create instant icon. So then go to the GPDK90 as a technology node. So we need to select the GPDK90. In GPDK90, we need to type the NMOS in the cell and click on the NMOS 1 volt and click on the symbol in the beam. We'll get the symbol of this NMOS and we need to close this icon. So close and hide. So here this is the NMOS. So we need to place in the schematic view. Again we need to go to the create instance and here we need to select the PMOS. So again height, and we need to select the PMOS. So the PMOS are connected at the top and the NMOS are connected at the bottom. So after that, we need to give the connecting wires. Give the connections by using the connecting wires. So these are the connections. So we need to give the connections. Then after, we need to give the VDD and the ground. So for that, we need to go to the analog library. So in the library, we need to select the analog library and type the VDD as in the cell and go to the symbol and click on OK. So the VDD will be appears. So we need to place it over here. And same for the ground. So after that, we need to create the pins. So for creating the pins, click on this icon, create pin icons. So give the names of the pins. If we select the input, if it name the input as an input pin, we need to select the direction as an input. If we name it as an output pin, then we need to select the output. So the pin will be created. After creating the pins, we need to give the input voltage inputs to the two inputs. For that, we need to go to the analog library and we need to give the V pulse as an input and click on symbol and click close. So we need to give the input over here. So for the input, we need to also connect the ground. So after connecting the inputs, click on this icon by pressing Q. Give the voltage values. The voltage 1 is 0, voltage 2 is 1.2 volt, and the period I have taken as 40 nanoseconds, and the pulse width is 20 nanoseconds. The period should be high than the pulse width. And click on apply and OK. For the next input also, for the second input also, we need to give the input values. So the period I have given for the second input is 80 nanoseconds and the pulse width is 40 nanoseconds. So the period is higher than the pulse width. Next, we need to give the delay time, rise time, and fall time. And click on apply and OK. So after that, we need to give the VDD voltage also to run the schematic. So VDD will be acts as a supply voltage to the circuit. So for that, analog library, click browse here and click on VDC. So click on VDC symbol and close. So the VDC symbol will be appears. Next, give the ground and VDD also for the VDC and click on Q icon. So for giving the DC voltage. The voltage I have given as 1.2 volts and click on apply and OK. So after constructing the schematic, next we need to check and save. So by checking and saving, so if there are any errors, it will be detected. And for the launch, we need to go to ADL, then after analysis, choose and give the in analysis, select the transient analysis, stop time. I'm giving as 100 nanoseconds and moderate. Click on apply and OK. Next, set up the click on the setup outputs icon, and from the schematic we need to select the inputs and outputs. So this is the A input, B input, and device and output. After selecting the inputs and outputs, so we need to go to apply and OK. Then we need to run the schematic simulation. So the output has been appeared. So we need to verify the outputs. First, we need to split current strip and trace. And I'm selecting the width as thick. Width as thick. So NAND gate output is the inversion of the AND gate. So when the inputs When the input both are 1, then the output will be 0. And when A input, one of the input is 0 and the other input is 1, then the output will be 1. And when A input is 1 and B input is 0, then the output will be 1. When both the conditions A and B inputs are 0, then the output will be 1. So this is the output for the NAND gate. Thank you.
So NAND gate advantages. NAND gates are the cost-effective devices and they have more storage capacities as per their size. So this gate offers the good replaceability, which measures that when the flash memory gets damaged, then it be replaced with a suitable component. So the memory ability of the NAND gate can substitute the huge files like USB drives, digital cameras, and the tablets. And it is also having the high endurance and the durability. So the applications of the NAND gate are, so the applications are used in the alarm circuits to the light detection radiation, and it is also employed in the freezer warning buzzer devices, and it is used in the automatic temperature regulation circuits, and it is also used in the burglar alarm. So this is the buzzer, which is a warning buzzer device, and this is the temperature regulation circuits, which is in the temperature regulation circuits the NAND gates are used, and this is also used in the burglar alarm also. Next, another universal gate is NOR gate. So the NOR gate is one of the universal gates. A NOR gate combines two basic logic gates, an OR gate and the NOT gate. So we can say it is an or not operation. It may have two or more inputs and an output. So the logical symbols of the NOR gate are shown in the figure. So this is the NOR gate logic. So for the OR gate, if we add the NOT gate, then it becomes the NOR gate. So this bubble represents that it is a NOT gate. So for the NOR gate, if we add the NOT gate, then it becomes the NOR gate. So the expression of the Y is A NOR, B NOR, C. There are two inputs only, hence it is A NOR B is the expression. So that is Y is equals to A plus B whole bar. So if the two inputs are zeros, then 0 plus 0 is 0, 0 bar becomes 1. And 0 plus 1 is 1, 1 bar becomes 0. And 1 plus 0 is 1, 1 bar becomes 0. And 1 plus 1 is 1, 1 bar becomes 0. So this is the NOR gate truth table. So the NOR gate is also called as the active low NAND gate. Active low AND gate, and the switching circuit of the NOR gate is shown in the figure. So this is the switching circuit of the A and B, and this is the bulb. So here, as the 0, 0 input are given, so for both the inputs are zeros, then the output will be high. So in this circuit, if the switches are not connected and we apply the voltage to it, then the bulb glows high. And if any one of the switch has been connected, then bulb glows low. So this is the circuit of the NOR gate. And the circuit diagram of the NOR gate will be having the PMOS which are connected in series, whereas NMOS connected in parallel. And these are the two inputs A and B and only one output. And these are the inputs which are given to the A and B. And here the output will be displayed, and this is the supply voltage to the whole circuit.
So for the construction of the NAND use, the PMOS are constructed in series and the NMOS are constructed in parallel. So to connect the PMOS and NMOS, first we need to place the components and we select the components. So for selecting the components, we need to go to the create instance and browse. And here also we need to select the GPDK ID. So we need to name the PMOS in the cell, and we need to select the symbol. The symbol appears here. After appearing it, we need to close and hide. So the PMOS symbol will be appears. We need to place in the schematic window. So that way the PMOS is selected and connected in series. And for the NMOS also, we need to go to the GPDK90 library, and the cell should be NMOS, and the wave should be symbol, and we need to hide. So here the NMOS symbol has been appears. So we need to place the NMOS symbol in the schematic window. Then after we need to give the connections by the connecting wires. So these are the two connecting wires. This is a thin wire and this will be the thick wire. So by using the connecting wires, we need to give the connections. After that, we need to give the VDD and the ground. So for that also we need to select create instance, browse, and we need to go to the analog library. So analog library, and in the analog library we need to type VDD symbol. The VDD symbol appears. We need to close and hide. So after that we need to give the connections of the ground also in the same way. So after that we need to give the pins. We need to create the pins. For creating the pins, we need to click on the create pin symbol and give the pin names. If we are giving the input pins, then give the pin names and the direction should be input. If we are giving the pin names as an output, then output pin name should be given here in the pin names and the direction should be output. So after that we need to hide. And the next is giving the inputs. So for giving the inputs, also we need to go to create instance, browse. After browsing in the analog library only, we need to type vpulse. So vpulse, and we need to click on the symbol. The symbol will be appears here and close and hide. So here the symbol will be appears. We need to place the symbol here and connect the ground to the symbol also. Vpulse also we need to connect the symbol. We need to connect the ground to the vpulse also. Next, after connecting the vpulse, we need to give the voltage values by clicking the Q as an instance. So here we need to give the voltage values. 1.2 volts as I have given the voltage to, and the period is 40 nanoseconds, and the pulse width is also 20 nanoseconds. So the period should be high. Then the pulse width. So apply and OK. And here the second input. For the second input also we need to give the voltage values. So the period is 80 nanoseconds and the pulse width is 40 nanoseconds. Delay time, rise time, fall time, all we need to give, and click on apply and OK. Then after we need to give the power supply to the circuit. For that, go to the create instance, analog library, type VDC. So VDC and we want height. So place over here and connect the VDD and ground to the VDC also, and now select this component and by pressing Q and give the DC voltage as 1 point. Apply and OK. After giving the all connections for the NOR gate, so first we need to do the second step. So if any error present, then it shows the error. So there are no errors. So first, then we need to run the schematic. So for that, launch ADL, choose the analysis. In analysis, choose and give the stop time. In the analysis, we need to select the transient analysis and select the stop time. I'm giving the stop time at 100 nanoseconds and moderate. Click on the enable, apply and OK. After that, we need to set up the outputs, input and outputs. From the schematic, we need to select the inputs and outputs. So input A, input B, and the output Y. After selecting the inputs and outputs, so we need to go to the select outputs, and here the inputs and outputs will be appears, and here we need to apply and OK. After that, again we need to run the simulation. The output appears here. So A and B and Y output. So I'm selecting the width as 6. So these are the inputs A and B and the output is 5. So for the inputs, both the inputs are 1. When both the inputs are 1, then the output is 0. If A is 0 and B is 1, then the output is 0. And if A is high logic 1 and B is low 0, then the output is also 0. When both the inputs are 0, then the output is high. So this is the NOR gate simulation, which is the inversion of OR gate.
NOR gate advantages. NOR gate logic gates are the cost-effective devices. These devices require the minimum space, less material for the construction, and the minimum complication too. So the applications are, these are used in the combinational circuits such as multiplexers, multipliers, half and full adders, and in also triple carry adders. And it is also used in the sequential circuits and in shift resistors also. So this is the multiplexer 16:1, and here this is the 32-bit sequential shift resistor. So the conclusion, the universal gates are the ones that can produce the any other logic or the Boolean expression. So the AND, NOR and NOT gate are the basic gates and can produce any logic or the Boolean expression. So by using the OR logic using AND plus NOT. So here the AND gates are NOT gates are used, and the NOT gates input outputs will be given to the NAND gate, AND gate, then it produces the, and it is also connected to the NOT gate, then it produces the output as a plus B. So again, AND logic using the NOR plus NOT. So NOT gate's outputs are given to the OR gate, and again it is connected to the NOT gate, then it becomes AND gate. So by using the logic gates NAND and NOR, we can construct any other logic gates. So hence those gates are known as an universal gates. Thank you.